Okay, welcome students. Have your clickers ready. We're going to do some clicking in a few minutes. There will be SI tonight, 3 o'clock to 3:50, and tomorrow. We'll have some homework. Hopefully I'll have that activated for you about 2 p.m. and it'll be due on Thursday. I want to review a few things or discuss a few things that I noticed in web courses over the weekend concerning homework 2, specifically problems 4 and 5, and good things. I was very happy to see that discussions were getting peppered up with questions and tips and queries from a lot of students. And that is very, very good. I love to see that. I love to get in there and mix it up. And the TAs are supposed to be doing that as well. And the discussion boards can be like a virtual study group or a virtual study partner. However, there were two really big threads, and I think one of them was longer. I had about, last time I looked at, about 40 posts in it, 40 replies, which is good. And I think the long one had a pretty undescriptive title. It just said homework 2, I think. Now remember, when you're doing this, I want you to set up a title for the thread that's a little bit more descriptive than that. So, for instance, homework 2, question 4, how do you get the distance? What's the formula? Or something like that, instead of just writing homework 2. And that'll make studying a little bit more efficient. Another thing that is, no matter what the descriptiveness level of the title, good or bad, I want you to read the threads carefully. In the long thread, one of the students posted a tip concerning the drop time question, number 5. You know, the student grabs the meter stick as it falls, and you're given a distance. And from that, you're supposed to figure out a drop time, which is kind of a brain burner. And a student, I can't remember who it was in this section or the other section, said, yeah, here's the actual formula. And it was a square root and had a bunch of stuff in there. And it was accurate. It was a good formula. And a lot of people apparently blazed past that and posted a question, I don't get number 5, even though the formula was right there. It was about 10 units down. So reply number 10 was in there and it looked good, but by about reply number 20, people were missing it. All right, so my admonition to you, or my advice to you, is read the threads carefully, and then you won't be duplicating stuff. Because there were some other people, and matter of fact, I even contributed to Malik's reply. I replied to his reply, and I wrote down the 2 formulas, one for question 4, one for question 5, and a little bit of discussion of them. And so if you read carefully, it'll help streamline your study experience. But in general, I love seeing all the level of activity. And so keep it up. It's going to be very helpful for you. Also, on the topic of iClickers, I am really starting to hate the iClicker mechanism in web courses. It is driving me. I refuse to allow it to drive me insane, but it keeps trying. So I have over 400 of you guys, but there's 600 of you in both, between the 2 sections. So not everybody's on yet, and some of those people that aren't on the list yet, they don't have their clickers. for whatever reason. But I know a lot of you are trying. So what I'm going to do tomorrow for office hours, usually I have them in room 158 where there's a lot of room to spread out and work on problems. And there's a big marker board and stuff. It's pretty nice. It's sunny. It's comfy chairs and stuff. But tomorrow I'll be in my regular office, so make a note of it. If you are getting frustrated by registering your iClicker and you haven't gotten any of the bonus points, and you bring it to class, you click in, but you're still not registered, come to my office hours tomorrow. And I'll be in my regular office, room 156, and I'll just meet with you one by one, and we'll just see if we can't register it through my computer. I think I could force my computer to do that. And as a matter of fact, I know that I can do that. And so come to the office hours between 11, any old time, between 11 and 1, and we'll try to get that done. The other thing that I will do is, if you're going to be on campus and you're really flailing and you're really desperate, but you can't actually come to my office hours in person, I'll set up an online office hours using the Adobe Connect software from 11 a.m. to 1 p.m. So even if you're out in Ocoee for the day, you can still use your web browser to get in and hopefully we can get your iClicker thing sorted out. Also, I know some of you work during the day on Wednesdays and so forth. So I'll try to set up another short office hour for clicking absentees only. If you're not on the list yet, it'll be tomorrow night. I'll set it up, and I'll set up a link inside Web Courses where you'll be able to participate that, and we'll try to thrash it out. So if you can't make it in person, you can't make it tomorrow in online Adobe Connect, then maybe tomorrow night. I'll set it up for like 8 or 9 o'clock or something. All right, any questions about all that stuff? All right, let's keep going. Let's do a recap from last time. We talked about distance polygons, the simplest one being the distance rectangle. Here's a velocity graph, velocity on the vertical axis, and I've got it marked out in 1.0 meter per second increments, positive and negative. For a constant velocity object, so it's cooking along at 2.0 meters per second, for some interval of time, delta t. And what I told you to do last time was construct the rectangle between the velocity graph itself and the time axis, and then straight line segments left and right. And that you can interpret that area of that rectangle as the distance, because it actually is the speed times the elapsed time delta t, or v times t. All right, and so that is the most basic interpretation of the area underneath the velocity versus time graph. And we did that last week, the distance rectangle. And then the next one that we did was the distance triangle, first of all for free fall. And so this is the diagram that we used. And let me get, oh, my cursor is tiny. I forgot to set my cursor back to gigantic. Sorry. Sorry, this little dot up here, that's my cursor. Sorry. Anyway, so we set it up for, starting up here at the origin where the time axis and the velocity axis intersect, 0, 0. You start, this is like being up on top of the library and dropping a water balloon. You start from rest. And then after 1 second of free fall, it's got 9.8 meters per second of downward speed. And so that means on this graph, negative 9.8 meters per second. It's below the time axis. All right? Another free fall second. Now you've got a total of negative 19.6. Increments of 9.8 meters per second, downward speed, every second of free fall. After 3 seconds, negative 29.4. After 4 seconds, negative 39.2. And again, we shaded in a triangle between the graph and the time axis. In this case, it's above the graph and below the time axis. The area of that is interpretable as the distance traveled. And to do that, we figured out the area by basically using 1/2 base times height, as is true for any triangle on a flat surface. So the base of the triangle is delta t. The height of the triangle is g delta t. And for the elapsed time, 4 seconds. And from that, we derived or put together this drop distance formula, right? 1/2 gt squared. And in this formula, g is positive 9.8 meters per second squared. And you had some homework doing simple calculations with that. By the way, your clicker questions, we'll be doing it in just a few minutes. You're actually going to do a calculation today with your iClicker. Or you're going to calculate a number and then enter it with your iClicker. And so hopefully you'll get the hang of it today for doing that particular task. Now, that's free fall. In the case of a generic acceleration, you have something similar. So for instance, a car that goes from 0 to some positive speed out on the road, like this little blue car here. Here it is again. The graph starts at the origin, Chelsea. It's 0, 0, so it starts at rest, and then you hit the gas, and you accelerate. And this one, a real car is not going to have a real straight line there. It might be a little wavy, because a real car, you hit the gas, it might, at certain RPMs, it might develop a little more horsepower, a little bit less horsepower. So you might not have equal acceleration all the way through, but we're kind of idealizing it here, okay? And so it eventually, after 4 seconds, let me move I can't even see my cursor. Gosh. All right. Okay, after 4 seconds, look at that thing. This is pathetic. All right, so all the way up here, it's at 3 meters per second after 5 seconds of travel. And the distance equation for this, distance triangle again, this is basically the same as the drop distance formula. The drop distance formula has the letter g in it simply because that's the nickname that we give to the acceleration due to gravity at the surface of Earth. The way that the gravitational field works, for a spherical surface like the Earth, if you're within a kilometer or a few kilometers of the surface, whether a few kilometers down in the sea or a few kilometers up at the top of Mount Everest, there's not a whole lot of variation in the strength of the gravitational acceleration. So it's considered a constant, 9.8 meters per second squared. So wherever you are, from the top of Mount Everest to the bottom of the deep blue sea, 9.8 meters per second squared. And by the way, if you go to 2 decimal points or 3 decimal points, you actually can measure variation in different parts of the Earth. And that is actually one way that geologists prospect for minerals. They measure for instance, iron ore is really heavy. And so if you find that the gravitational field over a certain part of a mountain range is extraordinarily high, measurably high in the third decimal point, you might say to yourself, I wonder if there's iron ore there, or maybe some other kind of ore that's valuable. So they actually use that. But to 1 decimal point, 9.8, yep, pretty much everywhere. Everywhere humans can go. Now, if you're out in space in the space shuttle or the space station, it's weaker up there, so it's less than 9.8. But here, wherever humans can go on Earth, it's 9.8. Generically speaking, this is the formula. D equals 1/2 AT squared. Now, we're going to do some calculations. And so I want you to get your calculator and your iClicker. By the way, I had a student send me a message this morning, or maybe yesterday, I guess. Dr. B, I got or my roommate, I think, has an iClicker, but it's the older one. It's not iClicker 2. Can we use it? The answer to that is no. The only way that we can do numeric input or letter input, alphanumeric input, is with iClicker 2. That's this one. It has a little display case, the little display screen on it. Okay. Also, if you're here for the first time with your clicker, what we want you to do is, here's your clicker question. Press and hold the power button until you get the flashing square, and then type in AA, and you'll get the session. You'll get Go Nitro, and you'll be able to vote. Okay, so here's the first question. What's the acceleration for this object? All right, and I want you to look at the graph. I did it very carefully. It is precise. The numbers are good. And I didn't write in every number on the time axis, but I did write a bunch on the velocity axis. And that's enough for you to get the acceleration. So go ahead and vote on that. And as I've mentioned before, when you're doing clicker questions, definitely talk to your neighbor if you feel like it. And if you have a friend, talk to your friend. If you don't have a friend sitting next to you, make a friend. And if nobody's sitting next to you, God bless you. Maybe sit with somebody next time if you want. Maria, good morning. While you guys are doing that, I'll have a piece of bacon. $30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, see what you guys have got. Uh-oh. We got a little bit of trouble here. We have a distribution of answers. A lot of you chose C, which is correct, but it looks like a bunch of you chose B, and B is not correct. What's wrong with B? That's the speed, velocity. That's not an acceleration. So B is out automatically. Anyway, the correct answer is C. And here's how you calculate it. delta V over delta T. Delta T is the width of the velocity of the distance triangle. And delta V is the height. It goes from 0 to 3 meters per second. And hey, you guys, do you remember what that quantity is from geometry class? The height divided by the width, the rise divided by the run. Slope, right? So the acceleration measures the slope of the velocity graph. The area underneath it is the accumulated distance of travel. Now, let's go to the second question. And how far does this object travel in the first 5 seconds of acceleration? Go ahead and vote for that. And you know, you guys, on a multiple choice question, remember, you just type your letter and it will automatically send. You can change your answer. If you answered A and you want to change it to C, go ahead and click in the letter C. And it will automatically send. "30 seconds. "15 seconds. "10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys have got. Uh-oh. We've got some splaining to do on this one as well. Here's the spread of answers. Now, that's not a disaster. All it means to me is that we should review the answer and how it is calculated. So let's look at it. Here's the answer, 7.5. And let's see, 48% of you got that correct. I guess you got tripped up on some of these other answers. Here's the calculation. Now, this one is base times height times 1/2, the triangle formula. And on this one, I want to draw your attention to the quantity denoted S, the seconds measurement unit. I can cancel it here, and down here in the meters per second denominator, and I'm left with meters. And that's good because it's a distance. I'm supposed to get some kind of distance unit. Meters is good. And you guys, that particular calculation is the distance triangle formula. Now, you can try the 1/2 AT squared using the calculation that you did in the first question. It's the same motion. And I should have mentioned that. This is the same as the previous question. Anyways, the previous question, the acceleration is 0.6 meters per second squared. And then 5 seconds quantity squared, you multiply that out, and you get the 7.5. And you could make a note that that equation, 1/2 AT squared, is a kinematics equation. You know, the triangle area, that's just geometry class. 1/2 AT squared on the right-hand side, that is physics class. That's kinematics, the science of motion. So let me pause for questions on this one. Okay, let's keep going. Now, here's a miscellaneous graph, and I'd like you to sketch this in your notes because we're going to have clicker question about this particular graph. And I did this one very carefully. It's just kind of a combo graph, a little smorgasbord of motion. The first time interval is regular acceleration. So for that, you would use the distance triangle formula. And I've shaded in the distance triangle here beneath the first part of the motion. Now the second time interval, you're at a constant velocity. The velocity graph levels off for 1 second. And so you use a distance, that says distance triangle. It's a typo. It should say second time interval is at constant velocity, so use a distance rectangle. Number 2 should mention a distance rectangle. And that's what I've got over here with the hatching from lower left to upper right. This is the distance rectangle in question. Now the third time interval from t equals 2 to t equals 4 seconds, you have a distance triangle and you have a distance rectangle, and they're right on top of each other. All right, it's a distance trapezoid if you want to think of it that way, but it's made up of a regular right triangle and a regular rectangle. All right, and if you compute those areas, you could figure out the total distance. Now I want you to sketch this diagram carefully because we're going to do a clicker question next. And you're going to type in a number for your answer. And it's going to be a little tricky. Let me move to the clicker question now. It's basically to calculate the total distance. So here's your clicker question. And that's the same diagram. All the numbers on this diagram are kosher. I measured them very carefully when I was creating the slide. And you have everything in there you need to figure out your distance rectangles and your distance triangles. Now, this is a numeric problem. So what I want you to do, you have to hit the blue refresh key on your calculator. Okay, it's a little blue key. I believe it's on the left. It has a little curly Q arrow sign, and it's colored blue. And hit that, and then you should get ready, and you should get, what do you get, the number 1? All right, so if you go up and down, you get the other numerals. Left and right will give you another number space. Also, so it's like a cheapo track phone like what I have, one of these little jobs. Where to type the letter C, you have to hit the key 3 times. Remember that? It's pathetic. This is what happens when you drop your iPhone, it gets smashed. You have to use a track phone. Anyway, so those are the numbers that are in there, and I'm going to turn the lights up for you because the decimal point in your iClicker is a menace. It is a menace to society. It's very tiny. It's very hard to see, even with the lights up. So I want you to answer something point something, 1 decimal point, 0.1 meter of precision in your answer. Right? So for those of you that are ed majors, this is what you would call a synthesis problem. You're putting together, you're synthesizing some concepts that before this were separate, you worked on separately. Now you're putting them all together. And that is a normal thing that I like to do and that you have to do in order to think. So let me hydrate up and you guys brainiac up. And do you want to walk around a little bit, Carolyn? And definitely chat with your neighbors if you feel like it. And Caroline is going to come around. That's good. Good. I see a lot of people interacting. This is actually a time when you guys really learn, when you're talking to each other and coaching each other. So if you're not sitting next to somebody next time and you see somebody in here that you know, sit with them next time. If you don't see anybody that you know, make a friend. If you want to have a friend, be a friend. Isn't that what they say? Yeah, when you type in your number, something point something, then you have to hit the send key. Because, with the hat. What's your name again? Sam. The reason is, Sam, the clicker software doesn't know how many places you're going to type in. So you have to tell it by hitting the send key. Very good. Very good. Good. "30 seconds. Mm-mm. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys have got here. All right. Now, let's go back to presentation mode. And let's take a look at your answers here. Okay, I can see by looking at it that 56% of you voted for 5.5. And actually, that is correct. Now, I want to show you something here. Because my cursor's not working good, I have to try to do this carefully. I want to show you some of the other answers, if I can. Uh-oh. You know what? I want you to look at this. Here's some answers. One student put in 44. And other thing, the previous class at the bottom of the list, there was one student that typed in 55. And the reason I'm bringing, so write down in your notes, 55. Correct answer is 5.5. Wrong answer, 55. Now, the reason I'm bringing that up to you is when we use clickers on the midterm, yes, we will be using clickers to type in calculations like this. maybe even this kind of a calculation, maybe even this very problem on the midterm. You never know. But what I do afterwards, I look at the raw data, and the raw data tells me the first thing you send and the last thing. And if you only send one answer, that's what shows up as your first and your last. Now what I do is I look at your last answer, and then if your answer is 55 instead of 5.5, I'll say to myself, you know, this guy blooped up the decimal point. I'll give him partial credit. Now, if you think about it, a Scantron test, it's either correct or it's incorrect. There's no partial credit on Scantrons. But with these problems, yeah. The calculation problems, you know, this might be a 2-point calculation. Sometimes I have 3 points and even 4-point calculations for something really tough. Usually towards the end of the semester, the really tough stuff. But for this one, I might give it 2 points. And if I saw the guy with 55, I might think, blooped up the decimal point, I'm going to give him 1 point instead of 0. All right? Now, I can do that because we have this iClicker. And that is why iClicker 1 is no good. You cannot do that. Because iClicker 1 is just an A, B, C, D, E type clicker. For us, we got to put in numbers. And if we do, on a test, you can get partial credit if you blow it. Now, so sometimes I'll see you know, like you might forget a factor of 1/2. Or you might put the decimal point, and that's common, believe it or not. That decimal point is a real menace. Anyways, let's look at the solution for this. Let me keep going here. All right. First interval. Now, I'm just going to tell you what I do. I did this visually, you know, mental arithmetic. I'm thinking, okay, the first interval, distance triangle, 1/2 base times height. I look at my base, that's 1 second. I look at my height, that's 1 second. 1/2 times 1 times 1 is 0.5. All right, so there's my first distance interval. Second distance interval is a rectangle, I use the distance rectangle. And again, for a rectangle, base times height. So I'm not thinking V delta T, although you can. It is equivalent. If I'm just looking at the graph, I'm thinking rectangles and triangles. And so for this one, the base is 1, the height is 1, base times height, 1. Unit meters. All right? Now the third interval is the one where I have kind of a combo calculation. I've got a distance rectangle, all right, and I got a distance rectangle. It's 2 seconds across from 2.00 seconds to 4.00, and it's 2 meters per second. No, it's 1 meter per second in height. Right? So 2 times 1 is 2. And that's the subcalculation for the distance rectangle. Now, sitting on top of that is a distance triangle for the acceleration. So when you're in this part of the motion, every second gets you a little bit of a distance rectangle and a little bit of a distance triangle in this part of the motion. So here's the distance triangle. It's 2 seconds across, and it's 2 meters per second tall. 1/2 base times height. 1/2 times 2 times 2 is equal to 2. Right? Total of 5.5 meters. All right. And so if you're wondering, Dr. B, how do I get that? Because I wasn't in the 56% that got that right. This is how you can do it. Now, what we're going to do on Thursday, I'm going to show you a fancy-looking formula that incorporates distance triangle, 1/2 AT squared, and V delta T technology in one formula. But here, We put it together in pieces and then or we took it apart, calculated each piece, and then we put it back together again. That's not bad. And if it works, it works. All right? All right, so that's kind of the generic kind of combo acceleration velocity curve. And that basically finishes up the chapter 1 topics. You can finish reading chapter 1 if you haven't already, and it'll all be a commentary on everything up to this point. Now, I want to push forward into chapter 2. It's fairly short. It basically centers on this concept of driving a Ferrari off a cliff. And you may say to yourself, Dr. B, Galileo, yeah, he was Italian, but there were no Ferraris in his day. Well, that is technically true, but he was thinking as if there were Ferraris that you could drive off a cliff. Now, let me set up this whole concept for you. In his day, the preeminent philosopher was Aristotle. And Aristotle is still pretty influential to our thinking about philosophy to this day. But in the day of Galileo, 400 years ago, so about the same time that Shakespeare was writing sonnets and plays and stuff, Galileo was working this stuff out, and Aristotle was very influential. But he had an argument, well, not with Aristotle, but with the students of Aristotle, the other professors of philosophy in Galileo's day all followed Aristotle, but Galileo felt that there was something about Aristotle's view of motion that was not quite kosher. So let's look at it. In Aristotle's view, his belief was that anything in motion requires a mover. In other words, there's got to be a force of some kind, either a push or a pull, for something to move. And if you do read Aristotle's Physics, his book called Physics, he describes all kinds of stuff like the flight of an arrow through the air. After it leaves the bow, Aristotle pictured the arrow as air coming from in front of the arrow, being pushed aside by the arrow, and swirling back behind the arrow and pushing it forward. And so it's very complicated and wrong. And so that was one of the problems of Aristotle's view. It's very complicated. Galileo simplified things, and he said, yes, there are forced motions, I agree, but there are also unforced motions which do not, that should be the word which instead of with, another typo. There are unforced motions which do not accelerate. So in other words, they neither slow down nor speed up, and they don't change direction. And just so you know, this figure here of a Ferrari going off a cliff, this is a trajectory. Let me get this. Gosh, where's my cursor? All right, get that out of the way. This picture here is from page 29 in the e-textbook, which is in chapter 2. All right, so Galileo's view was there's something else, Aristotle, that you've missed, and that is it is possible under certain conditions to have motion that continues in a straight line in the same direction at the same speedometer level. In other words, constant velocity. And without having a force acting on it. And Aristotle would have said, Galileo, you're out of here. But Galileo said, Professor Aristotle, I beg to differ. And so let's take a look at this frictional, this mythical place. All right, so item 3. So what Galileo did, and you can read this in his dialogues and so forth, his writings, He thought of a hypothetically frictionless horizontal plane that extended for a great distance. And on that frictionless plane, flat, horizontal, so it's not going downhill, it's not going uphill, it's just horizontal. An object is indifferent to being at rest or in a state of motion. In other words, if it's in motion, it'll persist at constant velocity. It doesn't care. It'll just keep going, cooking along until it leaves the plane. All right, and this is the state of motion that Aristotle would never have agreed to. But Galileo said, you know, until that Ferrari drives off the cliff or something, you know, it's going to keep going on this frictionless, hypothetical flat plane, neither uphill nor downhill. It's going to keep going until, and you know, he did visualize it rolling off the edge, something rolling off the edge of his plane, and then starting in a ballistic car, kind of like this car. What is this, Fast and Furious 7 or something like that? Can you imagine being the stunt driver that does this stunt? I didn't even know how they do that. If it was a real stunt or if it was computer generated. Anyways, Galileo was able to prove to his professor, Aristotle, and to all the other faculty mates at the University of Padua and all across Italy, all across Europe, that he was right, that this indifferent state must exist. And the way that he did that is what we're going to talk about now. And he used ramps. And his knowledge of acceleration, free fall acceleration, and not free fall. You know, a ramp is not free fall. It's on a ramp. It's constrained to a certain tilt. You know, it's not going straight down. Okay? So he knew, because of the physics of ramps and stuff, he was able to prove that Aristotle had to be incorrect and that he was correct. So let's start the proof. Here's a comment. And you can write this down. It's based on something from page 27 in the e-text. According to you and Aristotle, the object will move along the horizontal plane only if it experiences a certain amount of push force. So that's what Aristotle would have said. He would have said, yeah, fine, hypothetical plane, frictionless, nice. But if it's going at constant speed, there's got to be some kind of a push force. Not too big maybe, but it's going to have some kind of a force. You know, and an arrow doesn't take a whole lot of force from air to move from point A to point B. But he said there is a force, and it's got to have one. All right, so let's look at let's make a sketch of this now. All right, so here's what Aristotle would say. Okay, here's the hypothetical plane and a little car. And note down here at the bottom of the diagram, I say v equals constant. Okay, so it's constant speed. And Aristotle is saying, yeah, there's going to be a little bit of push force. So let's say that it's going to be something small, 0.02 metric units of force. And it's going to be in the direction of travel. So give it a little tiny arrow. And I've labeled this arrow, this vector, with a lowercase p and a little teeny arrow over the letter P to indicate that it's a vector. All right, so this is Aristotle's position. Yeah, you can have something on your, you know, Aristotle was a good guy, and actually Galileo liked Aristotle and respected Aristotle. It wasn't like Galileo, he was so argumentative. Did you ever know anybody that's like that? That no matter, yeah, I better not ask for show of hands. I see a guy in the back going, yeah, I know. You know, maybe you don't want to even think about it, but there's argumentative people in the world, and he had a chip on his shoulder, I guess, you know, and he was always ready for a scrap. He was always ready to scrap with somebody and battle it out, the battle on the high seas. But he liked Aristotle. In fact, Galileo did study Aristotle carefully and valued stuff. But in this area, he disagreed. And Aristotle was saying, okay, Galileo, yeah, but you're going to need a little bit of force. Let's call it 0.02. That's a pretty small number. So Galileo said, yeah, okay, good. So here's what Galileo's counter-argument is, okay? And we'll redraw the frictionless plane up a little higher. And Galileo said, yeah, okay, you've got a push force. It's pretty small. Whatever it is up there on that plane is going to have some downward weight force, all right? So I'm drawing in a big arrow. Now the weight force is going to be pretty big, all right? And so, for instance, Galileo might say, very nice conjecture, Professor Aristotle, but this car also has a bit of weight force, capital W. And let's say that it's 0.100 metric units of force. Now, I've made my two arrows in the ratio of 1 to 5. One of them's 50 pixels long, and one of them's 250 pixels long. All right, you try to make yours look about the same proportion as what I've got. All right. Now Galileo said, yeah, if this thing's got a weight force, now I'm up here on a mythical frictionless plane, and it's horizontal. It's neither tilted uphill nor downhill. All right, it's frictional, or it's horizontal. All right, and Galileo said, look, if it's really true what you're saying, Aristotle, about 0.02 units of force, I'm going to defeat you. And the way that he defeated him was by constructing a ramp. Now, how did he construct the ramp? He said the following: if I copy your push vector, P, so there's my copy, and if I copy the weight vector, capital W, and use them to make a right triangle, a ramp, then I can defeat your whole logic, Aristotle. Aristotle was great. He was a very logical guy. So was Galileo. And Galileo won the day. Here's how he did it. Make the vector P, the push force that you maintain exists, Professor Aristotle, make that the vertical part of a right triangle. And make the weight force vector the slope of a right triangle. Here it is. All right, now try to draw these in. All right. Now the way that you would draw this in, and here's a triangle kind of nested in there. Draw your P vector vertically somewhere over to the side, and then tilt your weight vector so that the very tail, oh boy, my cursor, I really need it now. Okay, right here, the tail of the weight vector is tail to tail with the tail of the push vector. And the push vector is downward. Make the tip of the weight vector over here, the arrow, the same level horizontally as the tip of the downward pointing push vector. And that's how you do it. All right? And it's explained in the book how you would do it with a piece of wood and make a wooden ramp. And Galileo said, all right, you say 0.02 for the push force, and I know that there's about 0.1 weight units of force. That gives me a ratio of height to hypotenuse about 1 to 5. All right? So all right triangles for which the height and the hypotenuse form a ratio of 1 to 5, they all look like this. They all have the same angles. All right, now that's all explained in chapter 2, and in the appendix as well. Now he said, all right, now the reason that this ramp is important, Professor Aristotle, is because if you now take the weight force and the push force and rotate them, so that now the push force is parallel to that ramp and the weight force is straight downward as it is. This push force, Aristotle, that you conjecture for the horizontal plane is actually the push force that gravity supplies, not in free fall, but on this ramp. And Galileo was able to say, if you tell me 0.02 units of force for a 0.1 weight force object, this ramp it doesn't have all the weight force down the ramp. It just has, if you're on this ramp, you accelerate, but it's kind of pokey. It's not very steep. But you'll accelerate because of gravity. And this is the amount of gravity that you get if you're on the ramp. And so Galileo said, all right, that's nice. You think that you need 0.02 on a horizontal plane, but no, my friend, no, professor, you need 0.02 on this ramp. To keep that thing from sliding down, you'd have to push uphill with 0.02, because gravity's pushing downhill with 0.02. So, Aristotle, you're out of here. 0.02 is no good ski. Horizontal plane, forget about it. And here's another way to write it. A flat plane will require less than this inclined plane. The flat plane, all right, even if it does require some force, it's going to be less than this. It's going to be less than 0.02. And here's the kicker. No matter how small you make that original force, the push force, Galileo or his deputy can always make a ramp to contradict you. It might not be very sharply tilted upward, but it'll still be a ramp. And if there's any kind of weight force, whatever you say, 0.002, 0.0002, anything you tell me, Aristotle, my ramps tell you that that is too big. Therefore, the only logical conclusion is that on a horizontal plane, to stay in motion at constant speed, constant direction, the force you need is 0. Therefore, Aristotle's busted. Mythbusters have prevailed for the day. All right, so Galileo technically was the first mythbuster. Okay, and this is one of his epic myth-busting events on Aristotle. So Aristotle, his idea that on a flat plane you need a little bit of push force, maybe not too much, but you need a little bit. Galileo said, dude, no, you don't need jack. You need zip, zap, zobo. You don't need anything. And sometimes we call this the inertial state or inertial motion. So let's just kind of and we'll put it into more modern terms now. An object with no forces acting on it will stay in a state of motion at constant speed, in a constant direction. Kind of like this hound dog on a skateboard. Raise your hand if you've ever actually seen, not on YouTube, but in real life, a hound dog. Wow. Where were you? I mean, is it your dog? Can your dog do that?
My cousin's dog's an American Bulldog,
And how about you?
my hometown's very bizarre. It's downtown, you see just about anything.
What's your hometown?
Amelia Island. It's just north of Jacksonville.
Oh, Amelia Island is very bizarre. Is that correct? Carolyn's from Jacksonville.
I've been there like once. It was interesting.
Caroline's been there once and it was interesting.
It's an interesting little town.
And your cousin has a bulldog that can do that? Man, my dog was never that smart. He was kind of a knucklehead. Anyways, this law, it actually, Sir Isaac Newton took this as his first law of motion. This whole idea that an object will remain in a state of constant direction, constant speed, motion, unless acted upon by another unbalanced force. Or it'll stay at rest. You know, Galileo and Aristotle both agreed about that. They both agreed about forces, you know, and something under a force. But it was this state, kind of in between those two, constant velocity state, inertial state, that Galileo developed and that Sir Isaac Newton made his first law of motion. Now we're up into chapter 3, the laws of motion. And we got a lot to talk about. Galileo was the professor who basically became the professor of Newton. I mean, not physically the professor, because Galileo died the year that Sir Isaac Newton was born. So, I mean, physically they weren't professor. But, you know, he built on the work of Galileo. And so here's how he would have written it. Every object retains its state of rest or its state of uniform straight line motion unless acted upon by an unbalanced force. So unless it, you know, so if you're up on that frictionless horizontal plane, you're not going to have any unbalanced force until you drive over the edge, and then gravity takes over. So, for instance, you're up on that mythical hypothetical plane, frictionless plane. You can't make a plane like that out of jello or water. It's got to have some rigidity to it. And that rigidity is an upward force, and gravity is the downward force, and they balance as long as you're on that frictionless plane. But once you get to the end and you keep going, then gravity takes over. Okay, and so that's what we call an unbalanced force at that point. Okay, so let's look at the example of an apple and an apple tree. And this is going to show the example, you know, you can think about a zillion examples of balanced forces, but this is a pretty good one. And actually, there's a myth about Sir Isaac Newton that he discovered the law of gravity, universal gravitation, after an apple. He was taking a nap out in the orchard, and an apple fell out of the apple tree and went bonk right on his coconut, and woke him up from his nap. And all of a sudden, oh, universal gravitation. That's what they say. And I don't think he ever said that, but I think that's what other people said. Anyway, so let's think about this apple. All right, stem attaches to the branch and attaches to the apple. Okay, so the stem is pulling upward. You can't make a stem out of water. It has to have some cohesive force. Okay, it has to be able to pull upwards. And that balances the gravitational weight force of the apple. All right, so no matter if you use metric newtons or metric units of force or any other unit of force, those two forces will balance until the stem weakens. And when the stem weakens, the balance fails. You know, like it dries out in the autumn and it gets a little brittle. And then if there's a gust of wind, it'll be too brittle to stay intact. It'll break and down it goes. And then once that happens, then there's an unbalanced force on the apple, gravity. 9.8 meters per second squared of acceleration. All right, so that's what happens. So that's a case of, so you can either have zero forces, you know, like you're way out in space, far away from the nearest galaxy, and there's no gravitational forces on you, and you're going around at constant speed, constant velocity. Or there are some forces on you, but they balance. And that would be the case here. Side note, an interesting case of forces that balance is forces that balance and produce constant velocity, constant speed, constant direction, is if you jump out of an airplane and you achieve terminal velocity. Raise your hand if you've ever jumped out of an airplane, skydove. If you're, all right. Now, what over there on the other side of Sarah? Sarah, how you doing over there? Good. Okay. Yeah, you, the skydiver. Yeah. What is your name? Melissa. Did you actually skydive or? Okay. I would be kind of even nervous about doing that. Your boyfriend? Boy. Oh, that's pretty good. Yeah, I bet you did feel safe. All right, you guys over here that skydove, did you tandem or did you actually skydive? Right. Have you skydived? Anybody skydove without a tandem? Nobody's done that. Well, here's what happens because like when you do when you do tandem, you actually do. You're just hooked up, but you're in free fall for a few seconds, right? Yeah. All right. So So tandem, I guess you can do this. It's just the two of you. All right. So if you're skydiving, either tandem or solo, you're going to accelerate downward. But here's a force that wants to push you upward. Air resistance. Right? You felt that, didn't you? I mean, it makes your clothes go upward, Everything is not attached. Originally, it's going to fly upward. Okay, so there's upward air resistance and downward gravity. Now, the key is that air resistance increases as the speed increases. All right? Now, when you first jump out of the plane, you're not falling too fast yet. You're getting air resistance, but it's not that big. But as you get faster, the air resistance gets bigger. And eventually, it'll be the same size as the weight force. And when that happens, you stop accelerating. That's your terminal velocity. Unless you change the surface area. So if you like tuck into a ball or aim yourself straight downward, so you're less area facing. So if you do a belly flop, you'll hit terminal velocity faster. But if you dive straight down like this, you'll hit terminal velocity. It'll take longer to do that, to hit terminal velocity. So anyways, so that's a case where you have forces acting, but they balance. And for a few seconds anyways, before you pull the ripcord, you're in constant velocity state, right? But balanced forces. All right, so let's keep going here. All right, now here's a picture. It says figure 219. I forgot to change this. It's from the old textbook, but let's take a look at it. Okay, the bus moves forward. You're standing in the bus. You're not, and I actually talk about this in the e-textbook, but with a different picture. You're standing in the aisle of the bus, and you're not holding on to anything left or right. You're just kind of standing there, and you're going down the road at 20, and if the driver hits the gas, the bus is suddenly going 25, and you're not buckled down and bolted in like the seats and everything, so you're still going 20. And that means you lurch backwards. Somebody's going to have to catch you from behind. Similarly, if you're going 20 and you're standing up straight, you're not holding on left and right. I mean, that's what I do when I'm in the bus. I make sure to hold on to something. But if you're not, and it slows down, all of a sudden you're going 20 and the bus is going 15, and you're heading towards the front now, and you're going to stumble forward. The second version is if the bus turns right. All right? You're going to bump. The bus turns off to the right. Your state of motion is straight ahead, even if he doesn't change the speed, if he just starts turning right at 20 and you're going straight at 20, that means you're going to bump into the left side of your left hip is going to bump into the seat, to your left. All right? So that's why, if you get on the shuttle bus, there's all kinds of handholds all over the place, just for that reason, so they can put people. If you're in a seat, it's not a big disaster. But if you're in the aisle, you got to stabilize yourself forward and aft. All right. Now here's another one. Whoops. All right. Throwing a football. This is one where, and actually we'll talk some more about this on Thursday. This arc, this is what we call a ballistic arc. And basically the arc of the football is the front and the back. The back and the front of the football's arc are just like the trajectory of a Ferrari going off a cliff. All right? Except that on the way up, it's like a Ferrari being launched into the cliff. And then on the back side, as it comes down to the receiver, it's like a Ferrari driving off a cliff. And so this one is underline the word separate. These are independent directions, and they are independent motions. And this also was something that Galileo, and he based it on his idea of inertia, that you could separate the motion like this into perpendicular directions, upwards and forwards, or right and left, and up and down. Now, Newton's second law, we'll finish with this. Newton's second law, this is the law that tells you what to do with unbalanced forces. Okay, if you do have unbalanced forces, you're in free fall, you accelerate. All right, so how do you handle this? It's all following Galileo's program, a mathematical structure. So first thing, you add up all the forces. And if anything doesn't balance, then that's what you call the net force. F subscript net. All right, so for instance, if you have Dwight Howard versus LeBron James pulling on a basketball, let's say that Dwight Howard pulls to the right with 100 metric units of force, and that LeBron James, being a weenie that he is, only pulls with 8. Actually, they're both weenies because they both don't play in Orlando. But anyways, LeBron James pulls leftward with 80 newtons, so he gets minus 80 units of force leftwards. So you add those up. 100 plus negative 80 is 20. And that's the rightward force. That's the net force. So then the next idea is, the more of that you have, the more acceleration. Also, the more mass you have, the less acceleration. So if you put the same push force on a loaded grocery cart versus a grocery cart that's empty, it's going to have a bigger acceleration on the empty grocery cart. So the formula that encodes all that, concepts 1 through 3, is this one, that the acceleration is the ratio of the net push force, or the net pull, divided by the number of kilograms. F net divided by m. A second version, basically equivalent, is F equals ma. F net equals ma. And so they're basically the same equation. And engineering majors know these out the wazoo. And on Thursday, we will have some more examples of Newton's second law. You're dismissed. Homework 3 will be activated at about 2 p.m. See you tomorrow. Or see you on Thursday. Where's my...